All right, this is Unit 2, Lesson 7, Linear Quadratic Systems. So our lesson essential question is, how can you solve a system of two equations or inequalities in which one is linear and one is quadratic? So at the end of this lesson, you will be able to solve linear quadratic systems. All right, example 1. Determine the number of solutions. How many solutions can there be for a linear quadratic system? How many real solutions does the system y equals x squared and y equals 2x have? So a graph is a great way to actually do this because you can easily see where the solutions are. The graph seems to show that the quadratic function and linear functions intersect at 2 points. So one there and one here. So therefore, this system has 2 real solutions. How many solutions can there be for a linear quadratic system? How does modifying the linear function in the system y equals x squared, y equals 2x plus b affect the number of solutions? So I can use the tool to explore different values of b. So if I look at this, so for b less than 1, or greater than negative 1, there's 1 solution, cross right here. So anything above this, they're going to have at least 1 solution. When b equals negative 1, there's 1 solution. The graph of y equals 2x minus 1 is tangent to the graph of y equals x squared. So you can see this. So tangent, basically what that's meaning is it's right next to each other. It butts up and it crosses at one point. But it actually just kind of almost like it's a sandwich. They sandwich together. Anything greater than that negative 1, though, you can see it crosses at 2 different points. Okay. When b is less than negative 1, so if I come down here at negative 2, we can see that the line actually does not intersect at all. So there would be no solutions. So visually inspecting the graph suggests that there is no way for a line to cross a parabola more than twice. Therefore, the system of linear functions and a quadratic function may have 0, 1, or 2 solutions. All right, so I'm going to determine the number of real solutions of the system y equals 3x squared and y equals 3x minus 2. Let me pull up Desmos real fast. Okay. So I have y equals 3x squared and y equals 3x minus 2. If I look at this, I can see that they do not cross. So that means there are no solutions. No real solutions. Okay. All right, example 2, solve a linear quadratic system using substitution. How can you use substitution to solve this system? 3x squared plus 3x minus 5 and 2x minus y equals 3. So the first equation provides an expression for y in terms of x. I substitute that expression into my second equation and I solve and factor. So x equals negative 1 and x equals 2/3 are solutions of this quadratic equation. If the graphs of the equation have 2 solutions, there are 2 points of intersection for the graph of the equations. So when x equals negative 1, y equals 2 times negative 1 minus 3 or negative 5. And when x equals 2/3, y equals 2 times 2/3 minus 3 or negative 5/3. So the solutions of the system are negative 1, negative 5, and 2/3, comma, negative 5/3. All right, so let's go ahead and try these out. It says solve each system by substitution. So I have y equals 2x squared minus 6x minus 8 and 2x minus y equals 16. So I'm going to substitute in for my y 2x squared minus 6x minus 8, and that's equal to 16. So when I simplify this, I get 2x minus 2x squared plus 6x plus 8 equals 16, which equals 2x squared plus 8x plus 8 equals 16. I need to move the 16 to the other side. So negative 2x squared plus 8x plus 8 minus 16 equals 0, which simplifies to 2x squared plus 8x minus 8. Okay, I can then factor out a negative 2, which gives me x squared minus 4x plus 4 equals 0. And that factors into x minus 2 times x minus 2 equals 0. Okay, or x minus 2 squared. So when I solve each of these, I have negative 2 equals 0. Well, that doesn't work. So I have x minus 2 equals 0. So x equals 2. Then I substitute that value back in and solve for y. So y equals 2 times 2 squared minus 6 times 2 minus 8. So y equals 2 squared is 4, 4 times 2 is 8, minus 12, minus 8. So y equals negative 12. So my value is 2, negative 12. Okay, so it's one solution. All right, letter B, y equals negative 3x squared plus x plus 4 and 4x minus y equals 2. So I'm going to go ahead and substitute in my value for y. 2. When I simplify this, I get 4x plus 3x squared minus x minus 4. I'm going to minus 2. That equals 0. So 4x minus x is 3x. So 3x squared plus 3x. And negative 4 minus 2 is negative 6. I can factor out a 3. So x squared plus x minus 2. Which factors into x minus 1, x plus 2. So then I have x equals 1 and x equals negative 2. I need to substitute those back in. So y1 equals negative 3, 1 squared, plus 1 plus 4. So that's 1 squared is 1 times negative 3. So negative 3 plus 1 plus 4. Negative 3 plus 1 is negative 2 plus 4 is 2. And I have y negative 2 equals negative 3, negative 2 squared, minus 2 plus 4. So negative 2 squared is 4. 4 times negative 3 is negative 12. Minus 2 plus 4 equals negative 14 plus 4, which is negative 10. So I have negative 2, negative 10, and 1, negative 2. All right, example number 3, applying a linear quadratic system. So Andrew kicks the ball up a hill for his dog. Okay, here's the puppy. Here's Andrew. He's going to kick the ball. Looks like he's throwing it, but he's actually kicking it. Leica, the dog, to chase. The hill is modeled by a line through the origin. The path of the ball is modeled by the quadratic function shown. Here's the quadratic function. Here's the line of the hill. How far does the ball travel horizontally? How far must Leica run up the hill to catch it? So if I graphed the quadratic, which is negative 0.5x squared plus 6x, and I graph the line y equals 0.5x, they meet right here at this point. So to create a system of equations and determine where the path of the ball intersects the hill, I can substitute in for y, so x equals 0 and x equals 11. Well, we know it goes through the origin. Okay? So the solution x equals 0 represents the horizontal distance in feet when Andrew kicks the ball. So I started at 0, 0. The solution x equals 11 represents the horizontal distance in feet when the ball lands on the hill. So the ball travels 11 feet horizontally. The route Leica runs can be modeled as the hypotenuse of a right triangle. So Leica runs approximately 12.3 feet to get the ball. So if here's 11 feet, this distance, here's my line at 5.5 feet, and then I find the hypotenuse of the triangle. All right, so let's try it. Revenue for the high school band concert is given by the function y equals negative 30x squared plus 250x, where x is the ticket price in dollars. The cost of the concert is given by the function y equals 490 minus 30x. At what ticket price will the band make enough revenue to cover their costs? So I have two equations, y equals negative 30x squared plus 250x, and y equals 490 minus 30x. Okay, so I'm going to go ahead and graph those. So y equals negative 30x squared plus 250x. Okay, and then y equals 490 minus 30x. So I'm looking at this point here, which is 7 to 80, which is 2.333420. Okay. So when ticket prices are between about $2.33 and $7, okay, they'll make enough revenue to cover their costs. So I'm looking at the X values, which were 2.333, which is about $2.33, and 7, that's where they cross. Okay. So the band will make enough revenue to cover their costs between ticket prices at $2.33 and $7. All right, example number 4, solve a linear quadratic system of inequalities. How can you solve this system of inequalities? Y is less than negative 2x squared plus 12x minus 10, and 4x plus y is greater than 4. Well, you can go ahead and graph them and then shade them. Okay. So I can graph the boundary line, quadratic boundary line. I complete the square to write the inequality in vertex form. Y plus 10 is less than negative 2 times x squared minus 6x. Y plus 10 minus 18 is less than negative 2 times x squared plus 6x plus 9. Y minus 8 is less than negative 2 times the quantity x minus 3 squared. So y is less than negative 2 times x minus 3 squared plus 8. The parabola has a vertex 3, 8. I find two symmetric points on either side of the vertex at x equals 2 and y equals 6. So 2, 6. And x equals 4, y equals 6, and 4, 6. And I sketch the graph of the quadratic inequality using these 3 points. Since y is less than negative 2x squared plus 12x minus 10, I shade the y values below the curve. I then graph the next boundary line. I solve the inequality for y to right in slope y-intercept form. I sketch the graph at the linear inequality using the slope and the y-intercept. I then shade the linear inequality. Since y is greater than negative 4x plus 4, I shade the y values above the line. So the solution is the green. So the region where the two shaded areas overlap holds the solution to the system. All right. So I need to solve the system of inequalities. Y is greater than x squared plus 6x minus 12. 3x minus y is greater than or equal to negative 8 using shading. So the first thing I notice is this line right here, the non-quadratic one, is actually going to be a solid line because there's an equal sign. I use the tool to graph each boundary, then use the slider to choose the solution region. So y is greater than x squared plus 6x minus 12. Okay, so when I graph this, I can put this in vertex form. Also use Desmos. Okay, and then 3x minus y is greater than or equal to negative 8. Okay, so here's my 2. So this is at 0, 8, and I don't have a good one. So 0, 8. 8. The other one was at negative 6, actually. It's got to be another nice, pretty. Negative 2.66, close to 3. Like there. When I'm graphing the quadratic, let's see, vertex is negative 3, negative 21. So that's down here somewhere. And then points 0.7 or negative 7.58. Negative 5, 10, 15. So somewhere around here-ish. Yeah, that's close enough. 7.5. Okay, close enough. All right, so I'm going to shade inside. Okay. So my y values, my y is greater than this. So I'm going to shade inside the red. Shade region. Shaded region. Okay. And then when I rewrite this, 3x minus y is greater than or equal to negative 8. When I actually do this, let me pull this up real fast. I'm actually going to solve for y. So 3x minus y, 8. I subtract 3x from both sides. I have to divide or multiply by negative 1, or negative 1, which causes me to flip my inequality sign. Okay, so y is less than, so that means I'm shading this portion right here. All right, example number 5. Using a system to solve an equation. Solve the equation x squared plus 9x minus 5 equals 4 minus 3x by writing a linear quadratic system and using the intersection features of a graphing calculator. So I'm going to graph the system, y equals x squared plus 9x minus 5. So I took the left side of the equation, I set it equal to y. Then I took the right side of the equation, I set it equal to y. The graphing calculator shows the curve and line intersect at x is approximately 0.71 and x is approximately negative 12.71. Okay. 12 and negative 10.7. So they want us to try it, solve the equation 3x squared minus 7x plus 4 equals 9 minus 2x by writing a linear quadratic system and using the intersection feature of a graphing calculator. So I'm going to set y equal to 3x squared minus 7x plus 4, and y equals 9 minus 2x, or y equals negative 2x plus 9. Okay. I'm going to go ahead and put that, let me do it here, 3x squared minus 7x plus 4 and negative 2x plus 9. Okay, I can see here and here are my 2 points where they cross. So negative 0.703 and 2.37. All right, so concept summary. Key features of linear quadratic systems. A linear quadratic system of equations. Words use substitution or elimination to solve the system. Graphs, if they don't touch, it's no solution. If they touch once, it's one solution. This is also known as a tangent. And if they touch twice, it's two solutions. Linear quadratic system of inequalities. Graph the linear and quadratic inequalities, considering whether the graph is solid or dotted. Use shading to identify the solution region. In this case, it's this solution here. And that is the end of Unit 2, Lesson 7.